Angelo. Okay, this work is about a survey on software quantum computing simulators. Yes, quantum computing is the child of another remarkable research area, information theory and quantum mechanics. The particularity here is that we have to apply the quantum mechanic concepts into the way that we execute computations. This is the main difference or the special thing here. For example, when we are using a register with n bits, classical bits, we just store one possible combination of all of them. When we are using the same amount of the fundamental building block in quantum computing, called qubit, we have to store all the combinations that we have with the same amount of qubits. There are several quantum computing models. The most popular is quantum circuits. This work is focused in this model. We have another one, very popular, adiabatic quantum computing. And another theoretical quantum computing models. Maybe interesting one is quantum Turing machine, proposed by David Deutsch as an extension of the well-known Turing machine. Well, with the possibility to play with real quantum devices, now they are available through cloud. We can play with them. There has been an explosion on software quantum simulators that run in classical computers. So the interest have a significant increment lately, and this is the reason to do this work. What do we have to consider when we are going to build one simulator of this? There are several aspects. Of course, we have to understand the fundamental building block here, which is the qubit. This is a unitary vector in two-dimensional Hilbert space. If we represent as a vector a classical bit, we are going to have a vector in the y direction to represent 0 and a vector in the x-axis direction to represent 1. When we use a qubit, we have a vector with a portion of 0 and a portion of 1. This is another particularity here, special thing. The representation is in bracket notation, where we can define a quantum state as a linear combination of the components. And they have to respect this rule here. The state, the possibilities, the combinations are multiplied by a coefficient called amplitude. This is called the wave function. So when we are going to build a simulator like this, we need to think, or we need to consider what we are going to store. So we need to store, of course, the states and the amplitudes. We store it in classical computer as a vector of the amplitude. Some of the simulators studies or analyzed in this survey use different techniques to store these elements. As a generalization, so we are going to have 2 powers n vector with 2 powers n elements representing all of the amplitudes, and maybe we have to have another data structure to store the states or the combination. The other important aspect to consider is how we change the state of those vectors, how we modify the quantum states. We do it using quantum gates. This is a transform that applied on a quantum register to change its previous state to the next one. So applying a quantum gate is a tensor product. We need to prepare the transform matrix. We store that gates in classical computers as matrix, spare matrix. So we need to prepare to reach the size of the quantum state vectors. Then we do the matrix multiplication. So this is one of the biggest issues here in building these simulators is the amount of memory they need to use to work. For example, if we are going to have a vector for 50 qubits, we need about 16 petabytes of memory, RAM memory. Well, the other important aspect is that when we measure, we apply the quantum algorithms, and when we are going to change the final result, the result is a normal classical register containing only zeros and ones. Another consideration we have to do in developing these quantum simulators are a special feature or characteristic of quantum mechanics. For example, superposition, which is the possibility to have a portion of one state and the portion of the second state. This is another specialty in this research area. Entanglement is another concept that comes from quantum mechanics, and this occurs when we cannot decompose a quantum state in their pure states. Because we use all of the combinations at the same time, there is a natural parallelism here in this quantum computing area. Okay, considering this, or taking all of these aspects into account, we start to test several quantum simulators. There are two kinds of quantum simulators. At least they use the same name to make reference to a real quantum device or a software package like we consider it in this work. So we focus only in software quantum simulators. as I said at the beginning, many or several real quantum devices are available, so the interest has increased lately to develop and to test quantum algorithms. We have tested some of them, some of the, of course, open source quantum simulators. Quantum is one of the simple one, but powerful. It is developed in C++, and the performance is increased using shared memory model of parallelism. They use OpenMP to accelerate the simulation. Quest is another open source quantum simulator. Is multi-threading, and the advantage of this simulator is accelerated using GPUs. All of the software we have tested are in the quantum circuit model, because this is the most popular model to do quantum computing. QRAC is another one that uses GPUs. This is because, as I showed you before, the way to change, to modify the quantum states is doing tensor products. So GPUs are very suitable to do this task. Intel Quantum Simulator is a very popular tool to test. Is developed in C++. The advantage of this simulator is that we can compile it, and it was developed taking into account the Intel compilers ecosystem. We can accelerate the performance, or improve the performance using one API, and it uses MKL library to improve its performance. There are another simulators called full stack, because they offer the whole environment to test quantum algorithm. Even the possibility to run the algorithm into real quantum devices. One of the popular one is HPCAPP. Is developed in C++, and is equivalent to another frameworks in HPC. KISSKIT, the popular KISSKIT from ABN, Project Q from ETH Zurich, Forest Simulator from Rigetti, Google Search, and Google Quantum Simulator. Lately, because this is one of our sponsors was included at the last moment, Atos MyQLen is a very simple one, is very limited in the number of qubits that we can simulate. However, they present an appliance, a very interesting system to improve the number of qubits we can use. And they provide also a quantum assembler language, which is very interesting to do this. Okay, after this survey, we realized that there are more than 100 tools around the internet. They are good tools to test without the problems of the real quantum devices, which are not very stable yet. They are limited in the number of qubits that we can use to simulate. And they are very useful to test code syntax and the quantum algorithms. They, of course, doesn't simulate real quantum states, but we can test quantum algorithms very well using these tools. The big issue, the big problem here is the amount of RAM needed to do the simulation, and this is another example. So, as future work, we are going to develop our own simulator, trying to apply a mixture of techniques in order to reduce the amount of needed memory in order to increase the amount of qubits we can use in some simulations. Among these techniques are the elimination of the less probable quantum states, maybe doing some vector compression, and maybe another more specific or complex techniques like using, for example, techniques of image compression here, like wavelet techniques, something like that.